Hello, my name is Kwang Yi, and I'm honored to present our paper titled Learning Training Dynamics for Active Learning. This is the joint work by Sungmin Ge, Kwang Yi Choi, and Hyungmin Byun with the corresponding author Buru Jang. This work was done at HyperConnect LLC, the subsidiary of Match Group and Tinder. We'll first skim through the preliminaries and the pilot study, and inspired by them, we'll share the theoretical results and our method. Finally, we'll briefly show the experimental results and analysis. Let's briefly skim over the typical definitions and settings, which comes from the fact that we always struggle with labeling budget in real life. So we often select the most useful data samples from unlabeled data and partially label them. So naturally, the typical setting would be randomly selecting a few hundred or a few thousand samples to be labeled so that we can train the initial model. Then often by using that model, we further choose additional samples to be labeled. Then ideally, the model's performance will improve as the labeled dataset increases. Then we repeat that process over and over again until the model is good enough for us. So there are many ways to choose the samples, and it's usually the diversity-based or the uncertainty-based, or sometimes both. The former focuses on choosing the subset to successfully capture the full unlabeled dataset, whereas the latter chooses the most uncertain samples, or choosing the samples that the model would be unsure about making the decision. We focused on the uncertainty-based and tried to focus on how we measure the data uncertainty. There are lots of literature that those unsure uncertain samples are indeed useful. So what we usually do is, after training, we run the model inference on all the unlabeled dataset and measure the loss or the classification probabilities. We call this using the outputs of the trained snapshot model, only using the frozen finished model. However, recent literature also says that the training dynamics are actually very important, which is the information generated during training. For example, we always look at the loss curves while training the model, right? So let's dive into this idea a little bit more. We conducted a pilot study to observe the information generated during training, the training dynamics, and we borrowed the long-tailed classification setting to control the level of uncertainty so that the majority class, like not all, but often contains certain samples, and vice versa, the minority class often containing uncertain samples. So we compare the model snapshot prediction at the final epoch t with the training dynamics, where we choose the simplest, which is the average of all the predictions during training. Intuitively, we expect that the easy samples to be learned by the model quickly so that the prediction quickly converges, and the result shows exactly that. If you look at the y-axis, the model snapshot, everything is converged on the final epoch, so we can't really distinguish blue and yellow, the certain and uncertain samples. However, if you look at the x-axis, we can clearly distinguish them. So to theoretically back this up, we proved two theorems. Theorem 1 says that the certain samples will converge quickly compared to the uncertain samples. And Theorem 2 says that the common functions such as entropy or margin can distinguish different convergence speeds even if they converge to the same prediction value in the end. So we talked about the training dynamics and their usefulness. Even if the easy and hard samples end up converging the same, their dynamics are different. However, we have to tackle the unlabeled samples where we can't really obtain their dynamics directly because they don't participate during training. So what we did was to simply train an additional module that predicts the training dynamics behavior to infer on the unlabeled samples. We compared our method with the 11 dataset settings and 8 baseline methods, and the performance is in fact good actually. The green and the blue ones are ours, and these show the relative improvement upon the random sampling case, and our works quite well on all the dataset settings that we've tried. We finish our talk by briefly going over our analysis. Our ablation studies show that our module is indeed effective. We also measure the quality of the training dynamics prediction module, which seems to be predicting well enough. This was Kwang Yi. Thank you for listening, and see you all at the poster.